Another day, another story. It didn't take long for the recent Foundational Questions Institute conference on the nature of time to delve into the purpose of life. The purpose of life, meeting co-organizer and Caltech cosmologist Sean Carroll said in his opening remarks, is to hydrogenate carbon dioxide. Well, there you have it. Carroll is one of the most reflective scientists I know and would never claim to reduce all of human existence to molecular disequilibrium. Still, it's nice to know your place in the grand scheme of things. The FQXi meeting had much to say about where we came from, and where we're headed. Last year, Carroll blogged the backstory of where his purpose of life line came from. He had bumped into Mike Russell of JPL, an expert on the origin of life, on an airplane and got to chatting about the role that living things play in the geochemical cycles of our planet. Russell was on hand at the FQXi conference, too, and elaborated on his engrossing thesis tracing our descent to inorganic chemical reactions. In Russell's picture, the primeval Earth looked uncannily like a giant bacterium. At the seafloor, in spots like the Lost City hydrothermal vents, the chemically reduced interior met the oxidized exterior, creating a state of chemical disequilibrium. Hydrogen bubbling up from the interior sought to combine with carbon dioxide dissolved from the atmosphere to form methane. But this reaction has a bottleneck because intermediate stages such as formaldehyde require an input of energy. See this helpful graph. A geochemical reaction known as serpentinization can push through the bottleneck, using metals such as iron as catalysts. But biological reactions are more efficient, and Russell mapped out a series of steps whereby serpentinization would evolve into membrane-encased cells. Evolution at this stage was not by natural selection, but by the spontaneous generation of complexity. The Darwinian version came later as information-bearing molecules arose. The scenario is commonly referred to as metabolism first, as opposed to genetics first. It is the proto-biological version of the principle that the way to a man's heart is through his stomach. The process would have given birth to two of the three kingdoms of life, bacteria and archaea. Russell suggested that life might have arisen multiple times on Earth and, indeed, on any planet with similar chemical imbalances. Phylogeny replicates geology. We also heard from two researchers who have looked at Darwinian evolution in action. Michael Lasig of the University of Cologne has studied seasonal flu patterns for clues to how evolution operates. The flu makes me wish intelligent design were true. We might have some hope of outwitting a designer, rather than remain locked in perpetual combat with a shape-shifting adversary. The influenza virus is continually improving its fitness. Lasig has found that, contrary to expectations, mutations that benefit the virus are actually quite common. If it is any consolation, the virus faces a Sisyphean task. Though continually improving, its fitness never actually gets any higher, because the very definition of fitness keeps changing under pressure from our own immune systems. Richard Lenski of Michigan State described his fascinating experiments on the evolution of E. coli. In 1988 he started to culture 12 populations of the bug and, since then, has seen 53,000 generations come and go, far more than the total number of human generations that has ever lived. Every 500, he freezes a sample of each population as a snapshot of evolutionary history. Lenski and his team find that the bacterium, like the flu virus, perpetually increases its fitness, meaning, in this case, its proficiency at consuming glucose and reproducing. As good as the organisms are at those two tasks, they can always get even better. The scope for improvement is essentially infinite. And as with flu, most of the genetic changes in E. coli occur by natural selection than by random genetic drift. A population of a given generation is more similar to the other independent populations than to its own ancestors. The coolest thing is that, while most of the lineages contented themselves with glucose, one eventually wised up to the fact that their petri dishes contained citrate, too, and developed a taste for it. When the researchers noticed this, they went into the freezer, pulled out earlier generations of that strain, and recultured them, replaying evolution to study how exactly the bacterium learned to broaden its diet. Lenski showed pictures of the giant stacks of petri dishes it took to watch history unfold again. Sympathetic murmurs of pity for the grad students spread through the FQXi audience. The team found that nearly 24 strains also managed to discover the citrate. Their newfound talent involved a complex rearrangement of bacterial DNA that did not come about in one mutation, but from a series of mutations. Early mutations having nothing to do with citrate were required to set the stage for the eventual citrate epiphany. To paraphrase John Lennon, evolutionary breakthroughs are what happens when you're making other plans. Lenski's work demonstrates that evolution is broadly repeatable. Geoffrey West of the Santa Fe Institute made much the same point when he showed the scaling relations that all living things follow. His and his colleagues' work has gotten a lot of attention in recent years, but this was the first time I'd seen him speak, and if I'd been a student, his talk might well have caused me to change majors. It's incredible, really, how such vastly different systems follow the same simple relations of size and energetics, reflecting economies of scale that all complex structures are subject to. West and Louise Betancourt have an article in our September issue on the scaling relations that describe cities, which look uncannily like those that govern organisms. Here are 3 of my favorites. An organism's lifespan is proportional to the 1/4 power of its mass. Its heart rate goes as the -1/4 power of its mass, so the total number of heartbeats is independent of mass, a universal value of about 1 billion beats for all of us. Use them wisely. The metabolic rate goes as the 3/4 power of body mass, in 3 spatial dimensions. More generally, it goes as the d+1 power. I take this as meaning that higher dimensional organisms achieve fewer economies of scale. People really do walk faster in cities, the walking speed scales with city size. In fact, the patterns were so impressive that they started to bring out my contrarian side. If I were a student, I'd probably start by seeing how universal they really are and what deviations represent. Toward the end of this talk, West went way beyond the Siam article and got into the implications for the near future of humanity, which he also talked about in an Edge interview this spring. West said he sees a recurring historical pattern. The pace of life accelerates, reaches a breaking point, and precipitates a major transition. A singularity, in which new technology or ways of doing things offer some respite. It doesn't last long before things pick up again, faster than ever. Over time, the acceleration accelerates. Transitions come faster and furiouser. Sustainability is elusive. We're basically all screwed. The alternative, that the super-exponential growth finally levels off for good, is fraught with dangers, too. Complexity theorist Raisa D'Souza of UC Davis argued in her talk that when you have coupled complex systems, any break in the growth trends tends to be accompanied by wild fluctuations. Modern society is predicated on growth. Stability is tantamount to collapse. I've never really bought into the singularity worries. I tend to think they over-extrapolate a very narrow kind of high-tech progress. The things that dictate our quality of life are mainly low-tech. Soft beds, flush toilets, smooth roads, fresh veggies. A single supermarket trip costs you more than an iPhone. But West did make a worrisome case that the accelerating pace of change goes way beyond Moore's law and pervades every corner of our lives. And so, as we reflect on the fascinating insights shared at the FQXi conference, we're reminded that the journey of understanding our place in the universe continues to unfold. From the origins of life to the patterns that govern living systems, these discussions shed light on the profound questions that drive scientific exploration. Stay tuned for more discoveries on the horizon. Thanks for watching.